Like the previous parts of Chapter 7, the situation here is that we have a pair of random variables x and y. But now our conditioning is simple. We learn y equals y, and the question is, what's the new PDF or PMF of x? When x and y are discrete, the situation is simple. We're interested in knowing the probability x is some value little x, given that y is some value little y. And we can define the conditional PMF of x given y to return precisely this probability, the conditional probability that x equals x given that y equals y. The notation for this function is as usual a capital P because it's a probability. Then we use the subscript capital X given capital Y to indicate that it's the PMF of X given Y. And then there's both an X and a Y that are dummy value arguments. While you can think of this conditional PMF as a function of both little x and little y, it's better to think of little y as a parameter, and for each value of little y, we have a different conditional PMF of x given y. For example, if y is Bernoulli, then P of x given y of x given 1, which represents the conditional probability x equals x given y equals 1, is one conditional PMF of x. Another conditional PMF of x would be the PMF of x given y equals 0. And it tells you that probably x equals little x given y equals 0. And the way to think of this is that each of these is a different conditional PMF of x. They're two different PMFs. From the definition of conditional probability, we can write these conditional PMFs as the probability of the joint event over the conditioning event. However, each of these quantities can be expressed in terms of PMFs. The numerator is the joint PMF of x and y at little x and little y, and the denominator is the PMF of y at little y. And here we have our sort of representation of the conditional PMF as the joint PMF divided by the marginal PMF. So this result is derived in this theorem. On the left side is the result we just derived on the last slide. The conditional PMF of x given y is the joint PMF of x and y divided by the marginal PMF of y. However, x and y are arbitrary variable names. We could have just as well conditioned on x equals x. In this case, we obtain the reversed result. The conditional PMF of y given x is the joint PMF of xy divided by the marginal PMF of x. Returning to the lower triangular joint PMF of x and y that we've seen before, this example asks us to find the PMF of y given x is little x for each little x. We know that our theorem says that the conditional PMF of y given x is equal to the joint PMF of x and y divided by the marginal PMF of x. So the key is finding this denominator, the marginal PMF of x. And we can do that by simply looking at this joint PMF and summing the columns so that we find, for instance, that the probability that x is 1 is this column sum, which is just equal to 1/4. And the probability x is 2 is this column sum. It's x is 2 and either x is 2 and y is 1, or x is 2 and y is 2. So we obtain 1/4. And similarly, the probability x is 3 is 1/4, 3/12, and the probability x is 4 is 1/4. Since the PMF of x is 1/4 for x equals 1, 2, 3, and 4, this is equal to 4 times the joint PMF of x and y for x equals 1, 2, 3, and 4. So it seems like we're all done, but it's worth noting that this is really 4 different conditional PMFs. For each x, y has non-zero probability on the integers 1 through x. For example, for x equals 4, y could take on the value 1, 2, 3, or 4. And what this function says is that these 4 values of y for x equals 4, namely these ones, will have their probability scaled up to add up to 1. So at x equals 4, we have the conditional PMF P of y given x of y given 4, and it's equal to 1/16 divided by 1/4, which is equal to 1/4 for y equals 1, 2, 3, and 4. And it's equal to 0 otherwise. At x equals 3, the conditional PMF of y given x of y given 3 is equal to 1/12 divided by 1/4, and that's equal to 1/3 for y equals 1, 2, 3, and 0 otherwise. Finally, we have 2 more. At x equals 2, we have the conditional PMF of y given x is 2, and this will be a half for y equals 1, 2, and 0 otherwise. And for x equals 1, we have the singleton PMF. In fact, we know if x equals 1, y has to be 1. And so all of the probability is on y equals 1. The key thing to keep in mind here is that this PMF corresponds to kind of normalizing these probabilities to sum to 1. Similarly, this conditional PMF at x equals 3 corresponds to renormalizing these probabilities to sum to 1. If I went too fast, this slide and the next slide repeat what I just did. So with discrete random variables, conditional PMFs were just a kind of restatement of conditional probabilities. But now we would like to think about continuous random variables x and y, and we'd like to condition on the event that y equals y. And now we face kind of the fundamental problem that the probability y equals y is 0 because y is continuous. However, when we define conditional probabilities, and for instance, we invented the conditional probability of A given B, we assumed P of B was greater than 0. On the other hand, we have lots of physical situations where we have a pair of continuous random variables and we appear to observe y equals little y for some little y. The solution to this is to sort of understand that when we observe a continuous random variable and we say y is little y, we're in fact more often than not observing that y is very, very close to little y. So we think of the event b as that y is in the interval from y to y plus dy for some small or infinitesimal dy. And similarly, we think of A as the event that x is very close to x. It's in the interval x to x plus dx. And now we can write the conditional probability of A given B as the joint probability P of A and B over P of B, and this is equal to the probability that x is in the interval around little x, and y is in the interval around little y, divided by the probability y is near little y. And now both numerator and denominator in this expression we can write in terms of density functions. The numerator is the joint PMF of x and y times dx times dy. And the denominator is the marginal PMF of y times dy. And we see we're kind of on the right track because these dy's cancel out, and what we obtain is the ratio of the joint PMF of x and y to the marginal PMF of y times dx. We see that this ratio we've obtained of the joint PMF to the marginal PMF of y is precisely what we defined here to be called the conditional PMF of x given y. Our interpretation of this ratio is that for each value of y, we have a different density function for x. So this density function in x times dx is the probability that the random variable x is in the interval x to x plus dx. And it's different, possibly, for each value of y. Specifically, the way to think of this is that the conditional PMF of x given y times dx is the probability that x is into the interval x to x plus dx given y equals y, where the conditioning y is equals little y is really shorthand for y is in the interval y to y plus dy. In any event, we should think of little y as a parameter, and that for each value of little y, we have a different conditional PDF of x. This is a good time to do an example. Here, x and y are continuous, and the joint PDF is uniform on this lower triangular region. The textbook asks us to find the conditional PDF of y given x for each possible value of x. So the solution to this is on the next two slides, and we'll leave that in the video and in the slide deck. But instead, to show the similarity and differences of this continuous problem relative to the discrete problem we solved a moment ago, I think here we'll solve a slightly different problem. Let's start by finding the conditional PDF of y given x for each value of x. From its definition, we can write the conditional PDF of y given x is equal to the joint PDF divided by the marginal PDF of x. So the first key step is to find this marginal PDF. Marginal PDF for x is reasonably straightforward. It's always, by definition, the integral of the joint PDF of x and y over all possible values of y. But of course, this is a different integral for each value of x. So the easy cases are when x is less than 0, and in this case, x is some value over here to the left of x equals 0, and the joint density doesn't exist there. So in fact, this integral will be 0. The other easy case to think about is that if x is greater than 1, then we're integrating the joint density along some y where there is no joint density, and again we have 0. And the interesting case that's left is x is between 0 and 1, and for x's between 0 and 1, we obtain, this is the integral from 0 to y, it corresponds to integrating along this line segment from 0, from y equals 0, up to this point where y is equal to x. So, so we have a typo here. Have to get the right kind of eraser. So this is to x, and now we plug in the joint density, which is 2 dy, and we obtain 2x. So this is 2x for 0 less than or equal to x less than or equal to 1. So now for each x between 0 and 1, we can use our definition of the conditional PDF of y given x, the joint PDF over the marginal PDF of x. Here we have the joint PDF. Here we have the marginal PDF, and we obtain f of y given x of y given x is equal to 2 over 2x equal to 1 over x. And this is for y's in the interval from y equals 0 to y equals x. So this is 0 less than or equal to y less than or equal to x. And of course, there is a 0 otherwise. So what we see in this problem is that for each value of x, y is uniform from 0 to x. This is kind of what we would expect because when we think about x's and y's along this segment, along this line, right, the joint PDF was uniform along this line. And so if we know that by specifying x, we lie on this line, then all of the y's ought to be uniformly distributed on this line. The other point to make is that uh, for each value of x, this is really quite a different PDF. It's uniform, but in fact, the interval it spreads over is different and the density is different. It just reminds you that the way to think of the conditional PDF of y given x is that it's a different PDF for every value of x. So this example actually asks for a lot of work. It asked us to find the conditional PDF of y given x, which is what we just found on the previous slide right here. It's 1 over x for y's between 0 and x, and x's between 0 and 1. But the problem also asked us to find for each value of y what the conditional PDF of x given y is. And the steps are essentially the same. First, you find the marginal PDF of y, and you integrate the joint PDF. But in this case, the limits are somewhat different. Remember, we have this triangular region for x's and y's, right? And when we condition on a particular value of y, we say like here is a particular value, little y. It implies that the x's we're going to see are in this interval. They run from this corner point here, the corner point where which in terms of y is y comma y, because this is the line here where x equals y, across to the other corner point here where x is equal to 1 and y is still y. So what we see is that for a given y, x has to be between y and 1. And that's how we obtain these limits of this integral, where we see that this joint PDF is non-zero. And the integral is actually simple. It's then 2 times 1 minus y. Finally, we use this marginal PDF by taking the ratio of the joint PDF to the marginal, and we see that the conditional PDF of x given y is slightly unattractive expression. It's 1 over 1 minus y, and it's for x's from y to 1. It's for x's on this stripe. And of course, the interpretation of that is that given a value of y, x is uniform from y to 1. So this example models the arrival times of telephone calls at a switch. We let x be the arrival time of the first call, the number of, and y be the arrival time of the second call. The first call has to arrive before the second call, so we have to have x less than y. And we see that this is in our probability model in that our joint PDF is non-zero only when x is less than y. As a result, this problem has some similarity to our last problem in that the xy pairs have to lie on a triangular region. But in this case, we first define the line y equals x, but we have to have y greater than or equal to x, which says that the triangular region is an upper triangle. And the other difference is that this triangular region goes up to x and y arbitrarily large. There's no upper bound. Let's start by finding the marginal PDF of x, which we obtain by integrating the joint PDF over all possible values of y. When we fix a value of x here, then in fact this integral is from along this red shaded region or pinkish region, which starts at y equals to x. And of course, this corresponds to the fact that y has to be greater than x. So this integral becomes the integral of from x to infinity. And we plug in the joint PDF, lambda squared e to the minus lambda y, and this is dy. And this is actually pretty simple. This is minus lambda e to the minus lambda y from x to infinity, and we obtain lambda e to the minus lambda x. So we see that in fact x is exponential with parameter lambda. Now we can write down the conditional PDF of y given x. Y given x. This is for all x is greater than or equal to 0. It's the joint PDF of x and y over the marginal PDF of x, and we obtain lambda squared e to the minus lambda y over lambda e to the minus lambda x, and this is lambda e to the minus lambda y minus x. And the point to keep in mind is that this is only valid for y greater than or equal to x. Although we're running out of room on this slide, it's worth noting that this is, in terms of y, it's a shifted exponential PDF. It's an exponential PDF with parameter lambda, but it starts at x. What this says is that y is equal to x plus another independent exponential random variable. So just to review, here's the solution in the textbook. We first found the marginal PDF of x by integrating over all y, starting at x and going to infinity, and then we found out that x was exponential. Then we took the ratio of the joint PDF over the marginal PDF, and we found out that y is a shifted exponential that starts at x and then goes to infinity. The second half of the problem asks you to find the conditional PDF of x given y. Probably before you look at this solution, you should go and see if you can work it out yourself. Although there's some algebra here, it's not actually all that complicated. I'll pause here to give you a chance to stop the video and go do this on your own. Okay, I hope you did this on your own, but whether you did or didn't, here's how the solution works. First, you find the PDF of y, and you integrate the joint PDF over all values of x. In this case, all values of x means from 0 to y, because we still are subject to the triangle where x has to be less than or equal to y. When you do this integral, it doesn't actually have any x in it. So in fact, we obtain that y has this PDF, and this is actually an Erlang PDF. There's a reason for that, and maybe we'll talk about that in the sums of random variables chapter. Finally, the next step is that we find the conditional PDF of x given y by taking the joint PDF and dividing by the marginal. And when you take the ratio of these two expressions, you see that the conditional PDF of x is simply 1 over y from x is from 0 to y. So what we learn is that if the second telephone call arrives at time little y, then the first call was uniformly equally likely to be anywhere in the interval from 0 to y. As a side note, I can't help but mention that this problem is connected to an earlier part of the book where we represented the arrivals of telephone calls at a switch by a Poisson random variable n tau, and it had parameters, a parameter lambda tau, the expected value, and it was the number of calls in 0 to tau in an interval of length tau. So in fact, this model for the arrival time of the first call and the second time is indeed exactly the same Poisson model, but just expressed in terms of these random variables of the arrival times. So far, we focused on finding conditional distributions from the joint distribution, but we could also use conditional distributions to derive joint distributions. By rearranging the definition of the conditional PMF, we can write that the joint PMF is the product of the conditional PMF of y given x times the marginal PMF of x. Or we could write the joint PMF is the conditional PMF of x given y times the marginal PMF of y. When we think about the events A, that x equals x, and B, that y equals y, we see that this theorem is just a restatement of an old friend, that the joint probability of A and B can be written as the probability of B given A times probability of A, or as the probability of A given B times the probability of B. While the derivation of the conditional PDF was more complicated, in fact, we arrived at an equivalent ratio as in the discrete case, and the result is, once again, we can represent the joint PDF as a product of a conditional PDF and a marginal PDF. Specifically, we have that the joint PDF of x and y is the conditional PDF of y given x times the marginal PDF of x, or it's the conditional PDF of x given y times the marginal PDF of y. This algebraic kind of similarity to the discrete case is useful and easy to remember. Now that we have these theorems where we can synthesize a joint PMF from a conditional and a marginal, or a joint PDF from a conditional and marginal, it's good to go back and revisit our definitions of independence. Recall that we said that for discrete random variables, x and y are independent if the joint PMF is product of the marginal PMFs. Similarly, if x and y are independent and they're continuous random variables, the joint PDF was the product of the marginal of x times the marginal of y. And now if we think about what we had before, we had, for example, in the discrete case, the joint PMF was the conditional PMF of x given y times the PMF of y. And if they're independent, This would be the PMF of x times the PMF of y. So what we see is that by independence, if it has to be true that the conditional PMF of x given y is equal to the PMF of x. The same logic applies to the discontinuous case. For continuous x and y, independence says that the conditional PMF of x given y has to equal the marginal PMF of x. And of course, there's equivalent statements for the conditional PMF of y given x and conditional PDF of y given x. The key idea here is that when x and y are independent, learning what the value of y is doesn't change the PMF of x. The PMF of x stays the same for every observation y. It's always the marginal PMF. Similarly, when x and y are continuous, learning the value of y doesn't change what the the PDF of x is. The PDF of x for every value of y is always just the marginal PDF. That's the idea of independence. Learning one of the random variables doesn't change your knowledge of the distribution of the other random variable. So if my words seem jumbled in the last slide, here's the theorem that summarizes these results. If you want to make sure you're up to speed, work out the solution to this quiz before you go to the next slide and look at the answer.